Have you ever been driving across a massive bridge, looked up at those giant concrete or steel beams and wondered, why didn't they just make this one giant super long piece? It seems like it would be stronger, right? Just one solid structure spanning the entire gap. But in reality, some of the longest, highest bridges in the world are built in sections, almost like a massive Lego set. Why is that? Well, the answer is a fascinating mix of physics, engineering genius, and a whole lot of practical thinking. Let's start with the biggest, most invisible force our planet throws at everything: temperature. You might not feel it, but materials like steel and concrete are constantly expanding when they get hot and contracting when they get cold. This is called thermal expansion and contraction. Now, imagine a bridge that's a single mile-long piece of steel. On a hot summer day, that steel wants to expand. If it has nowhere to go, it will start to buckle and warp under its own incredible internal pressure. It's like trying to squeeze a spring that doesn't want to be squeezed. The force is immense. In the winter, the opposite happens. The steel contracts, pulling on its anchor points with enough force to potentially crack the foundations or even itself. It's a battle against nature that the bridge would inevitably lose. To solve this, engineers use something called expansion joints. These are those metal, tooth-like gaps you see and feel when you drive over a bridge. They look simple, but they are incredibly important. These joints create a small, intentional gap between the sections of the bridge. When the sections expand in the heat, they move into this gap, safely releasing the pressure. When they contract in the cold, the gap simply gets a little wider. This allows the bridge to breathe with the changing seasons, preventing the buildup of catastrophic stress. Building in sections is what makes these life-saving expansion joints possible. Without them, most long-span bridges simply couldn't exist. But it's not just about temperature. Let's think about the sheer practicality of building one of these giants. Imagine trying to manufacture a single 2,000-foot-long multi-ton steel girder. Where would you even make it? What kind of factory is that big? And even if you could make it, how on earth would you transport it? You can't exactly put it on the back of a truck and drive it down the highway. The logistics would be an absolute nightmare. It would require specialized roads, unimaginable cranes, and would be astronomically expensive, if not physically impossible. Instead, building in segments is a masterclass in efficiency. These smaller, more manageable sections can be manufactured off-site in a controlled factory environment. This ensures higher quality, better precision, and stricter safety standards than trying to build everything out in the open, exposed to the elements. These prefabricated segments are then transported to the construction site by truck, train, or barge. It's a process that has been refined over decades. Once on site, powerful cranes can lift each section into place, where it's then carefully secured to the previous one. This piece-by-piece assembly method, known as segmental construction, is faster, safer, and far more cost-effective. It allows for a continuous, assembly line-like workflow. This method also offers incredible versatility, especially for high bridges built over deep valleys or wide bodies of water. For these challenging locations, a technique called balanced cantilever construction is often used. Picture this. A pier, or a support column, is built in the middle of the gap. Then, segments are attached to the pier on opposite sides, one after the other. It's like building the bridge outwards from the middle, keeping it perfectly balanced with each new piece. One segment is added to the left, then one to the right, maintaining equilibrium. This allows construction to proceed without needing extensive scaffolding or support structures rising from the ground or water below, which would be impractical or impossible in deep water or rugged terrain. The bridge essentially supports itself as it's being built. Furthermore, building in sections provides crucial flexibility and resilience against other forces, not just temperature. Think about the ground itself. It's not perfectly static. Over time, the foundations of a bridge can settle slightly. If the bridge were one rigid piece, this settling could create immense stress and cause it to crack. But a segmental bridge has a little bit of give. The joints between the sections can accommodate minor movements, making the entire structure more durable and adaptable over its lifespan. The same principle applies to dynamic loads, like wind and even the vibrations from traffic. A super-rigid single-piece structure could be more susceptible to resonating with certain wind frequencies, which is a terrifying prospect for any engineer. The infamous Tacoma Narrows Bridge collapse is a stark reminder of that danger. By building in sections, engineers can design a structure that is better able to dampen vibrations and flex safely under stress, distributing the load more effectively across the entire bridge. So, the next time you're on a magnificent bridge, take a moment to appreciate its design. It's not just a single, solid path. It's a dynamic, breathing structure made of dozens or even hundreds of individual pieces working together in perfect harmony. This segmental design is a brilliant solution that battles the forces of nature, overcomes incredible logistical hurdles, and ensures the bridge can stand strong and safe for generations. It's a testament to human ingenuity, proving that sometimes the strongest things are not those that are rigid and unyielding, but those that are flexible and built to adapt. Thanks so much for watching. If you found this interesting, don't forget to hit that like button and subscribe for more deep dives into the world of engineering and design. See you in the next one.